Salam and welcome everyone. So today we're going to be working on the question on the screen that says, consider a container of 250 centimeter cube that is divided into two compartments of equal size. In the left compartment, there is argon at 100 kilopascal and 0 degrees Celsius. In the right compartment, there is neon at the same temperature and pressure. Calculate the entropy and Gibbs energy of mixing when the partition is removed. Assume the gases are perfect. So as you can see, this is a very long question. And one thing you would quickly observe that this question is in steps. And for those of you who don't know, this is a question from chapter 5, Simple Mixtures of Atkins Physical Chemistry 11th edition textbook. And it is question 4B in the exercises. So they said, consider a container of volume 250 centimeter cube that is divided into two compartments of equal sizes. In the left compartment, there is argon at 100 kilopascal and 0 degrees, and in the right compartment there is neon at the same temperature and pressure. So knowing this, I can just simply do this. So let's say this is a compartment that we're working with. So this is a compartment or the container or the box, whatever you want to call it. Sorry, I don't have the best drawing. We're told that that compartment is divided into two equal size. So when you divide it into two equal sizes, it's not equal. So when you divide it into two equal sizes, is you would have the left compartment where there's argon and the right compartment where there is neon. And we're told that the pressure of argon, okay, is going to be 100 kilopascal. And the temperature of argon is also T. Temperature of argon is just simply 0 degrees Celsius. And of course, temperature, whenever you're calculating, you just add 273.15 to whatever the degree Celsius value is in order for you to get it in Kelvin. So we have 0 degrees Celsius, so 273.15 plus 0. So we have the temperature of argon to simply be 273.15 Kelvin. So we have both the pressure of argon and the temperature of argon. And then you also have for neon, so the pressure of neon to be 100 kilopascal and the temperature of neon to be 0 degrees Celsius. So the temperature of neon is 273.15 plus 0. So temperature of neon is 273.15 Kelvin. So that's basically the value for temperature as well as the value for pressure for both of them in the compartment. Let's not forget that we're also told the volume of the container to be 250 centimeter cube. So the volume of the container, so the full box is 250 centimeter cube. That is the volume. So one thing you can do is for us again to redraw a container in order for us to be able to determine what the volume for each for each compartment. So the total volume is 240. If you divide it in two equal halves, what you just end up having would just be 250, okay, centimeter cube divided by 2. So the volume of each of them would just simply be 125 centimeter cube. Because if something has, let's say a bottle can take a bottle has the capacity to handle like 1 liter volume. If you cut the bottle into two equal halves, you end up seeing that the volume of the water or whatever is in the bottle can only take half of what it was able to contain in the first place, right? And that way to look at it, I know that we're advanced. I just want to write things out for sometimes struggling students. It's kind of hard for them to visualize certain things. So for example, we see this one right here to be the length of the box. Remember, volume is just simply length times breadth times height. So we have A to be the length or to be whatever it is. We have B, it's a cube, to be the breadth, and we have C to be the height. Okay, so you can see here that volume is just going to be A times B times C. When you cut it into two equal halves, divide by 2 here, you divide by 2 here, you just end up with half of the volume. So that's it, because of course we're dividing this A but the length of B still remains the same, and the height of the container still remains the same. So the breast still remains the same, and the height still remains the same, but the length is divided into two. So that's basically why our new volume for each one of the compartments will simply be that. Don't know why this is appearing, but we're just gonna move on. So the new volume, of argon is just simply going to be 125 centimeter cube, and the new volume of the right compartment, so that is the volume of neon, to be also 125 centimeter cube. So we have all the information that we need. We've written it out. So they said calculate the entropy and Gibbs energy of mixing when the partition is removed. So basically, when we remove whatever this is, the partition that was separating it, that was put in half of the box, whenever we remove it, argon on the left side and then neon on the right side are going to end up mixing. So we're told to determine the Gibbs energy of mixing as well as the entropy of mixing by assuming both argon and neon to be perfect gases. So we're told to determine the Gibbs energy of mixing as well as the entropy of mixing. So that is basically what we're doing after the partition of the container has been removed. Has been removed, which of course results in the mixing of the two gases. So that's basically it. Now I've written out the foundation for what we're supposed to do. I have done the breaking down of every single value that we are given, as well as broken down the question. Now, for those of you who don't know, if you check your chapter 5 of the Asking Physical Chemistry 11th edition textbook, we're going to be using the Gibbs energy of mixing, which is just simply Gibbs energy of mixing is simply the number of moles of the first component. So let's say in this, the first component, meaning one of the components in the mixture, we're dealing with the binary mixture, meaning a mixture between two um, different components. So in this case, mixture between neon and argon. So which I'm just going to use the general formula, and then we're going to um, d- make it more specific as we solve along. So the Gibbs energy of mixing is just the number of moles of component A multiplied by RT, or gas A multiplied by RT, is equal to ln the partial pressure of component A, or gas A, okay, divided by the total pressure, okay, plus the number of moles of component B, or gas B, multiplied by R times T ln the partial pressure of gas B, or component B, divided by the total pressure. So that's what's going on here. That's one way. Another way you can look at it is if you're given a situation where you're dealing with mole fraction, okay? So this first one, you use this first one when you're given the regular ideal gas parameters, right? For example, if you're given the number of moles, the temperature, the pressure, or if you can solve for it, you use that one. In situations where you're not given the temperature, in situation where you're not given the pressure, and you're also not given other parameters, but you're given the mole fraction, okay? Mole fraction, you have a different formula that you use. The formula would be, and I'm giving you this just because students are different. Another student may be given a question where they have to use mole fraction. So the mole fraction formula for Gibbs energy of mixing is just simply nRT. Okay, so N is the total number of moles, not any other number of moles, the total number of moles. So you can even say N sub T multiplied by the mole fraction of gas A on component A multiplied by ln of the mole fraction of component A, or gas A, plus the mole fraction of component B multiplied by ln of the mole fraction of component B, or gas B. So in this case, this is when you're really just dealing with mole fractions, so that's basically what this is. Yeah, that's it. That's about it. So in this case, of course, if you look at our work, we're given volume, we're given pressure, we're given temperature, then we don't have to do anything with the second formula that involves the use of mole fraction. So from my explanation so far, you already know we're not going to be using the mole fraction formula. We're going to be using the first one that I explained. We have N sub A multiplied by R times T ln PA sub PT. So yeah, that's basically what that is. Now, we have the R, because R is just simply gas constant. We have the temperature. We have the pressure of the argon. we have the pressure of the neon. So rewriting this formula to match our work. So Gibbs energy of mixing is just simply going to be the number of moles of argon multiplied by the gas constant multiplied by the temperature. You can also say temperature of argon. The temperature is literally the same. It doesn't change at all. So yeah, it's literally the same. Multiplied by ln of the partial pressure of argon divided by the total pressure plus the number of moles of neon, okay, multiplied by R, multiplied by the temperature of neon, okay, ln the partial pressure of neon divided by the total pressure. So that is what we have. So all we can simply do is for us to determine the value of the number of moles. So since we've been given the pressure, the temperature, we know what the gas constant is, we know what the volume is, we can just simply determine the number of moles. But the issue is, since we're scientists, we have to make sure that we don't always think about things only in one way. Another way we can look at it is that since we know that the gases are perfect and we're assuming they're perfect, we know PV is equals to nRT. Rather than solving for the number of moles and then substituting and then multiply by R, multiply by T, we already know that PV is equals to nRT. So PV is equals to nRT can be substituted for just PV. So what I'm saying is PV is equals to nRT. So the pressure of argon multiplied by the volume of argon, okay, is equal to the number of moles of argon multiplied by R multiplied by the temperature of argon. So since this is what we have here, rather than us determining the number of moles and making our work longer, so one thing we can just simply do is to just substitute PV in this part, and then we do the same thing for neon as well. Remember, for neon, the pressure, okay, of neon, okay, multiplied by the volume of neon is going to equal the number of moles of neon, okay, multiplied by R, multiplied by the temperature of neon. So we can just simply substitute. So for this question, we can rewrite our formula for the Gibbs energy of mixing by substituting PV into this part of the information here for argon, and then substituting the PV of neon into this information here as well. So the Gibbs energy of mixing ends up becoming the pressure of argon multiplied by the volume of argon, okay, ln the pressure of argon divided by the total pressure, okay, plus the pressure of neon, okay, multiplied by the volume of neon, ln the pressure of neon divided by, so the partial pressure of neon divided by the total pressure of both neon and argon. So yeah, this is actually the formula we use. It makes our work easier because we can just simply substitute to make our work neater. This is perfectly allowed to switch formulas when you already know fundamental information like the gas constant, so you can substitute. This is just like doing algebra, basically. So yeah, this is what we're going to be using. Now, we have the pressure for argon, we have the volume for argon, we have the partial pressure of argon, we have everything else except for the total pressure. And for those of you who don't know, if you remember Dalton's law of partial pressures, the total pressure in a mixture is equivalent to the sum of each individual partial pressures of each one of the components. So in this case, the total pressure would just be the partial pressure of argon plus the partial pressure of neon. So that's simply going to be the total pressure would be, the partial pressure of argon is 100 kilopascal, okay? So 100 kilopascal, and that is also the value for the partial pressure for neon, plus 100 kilopascal. So the total pressure is just simply going to be 200 kilopascal. So we have this value here. Now we have another thing that we have to manage in this case. We have to remember that the volume is actually, for each one of them, is just 125 centimeter cube. And whenever we see pascal, we have to make sure that the volume that we're dealing with is in meter cube. So we have to convert from centimeter cube to meter cube. And if you remember, 1 meter cube is equivalent to 1 times 10 raised to the power of negative 6 centimeter cube. Because again, if you remember your foundational units, you know that 100 centimeter is equivalent to 1 meter. When you cube both sides of it to be able to get the cube, on the right side you have 1 meter cube, because 1 meter times 1 meter times 1 meter is 1 meter cube. But in this left side, we have 100 times 100 times 100, that's just going to give you 1 times 10 raised to the power of 6. Centimeter times centimeter times centimeter will give you centimeter cube. Sorry, I just saw I made an error here. So it is not 1 meter cube is equivalent to 1 times 10 to the power of negative 6. Is 1 meter cube is equivalent to 1 times 10 to the power of 6, not negative 6. So yeah, that is what we have here. So hence 125, the volume, okay, is just going to be 125 centimeter cube to meter cube will just simply be 125 times 10 raised to the power of negative 6 meter cube. So that's just going to be the conversion. Again, for any student who is struggling, it's just simply 125 centimeter, okay, is equal to x, while 1 times 10 to the power of 6 centimeter cube is equal to 1 meter cube. If we solve for x in this case, we end up with x is equal to 125 centimeter times, okay, so 125 centimeter cube, sorry, times 1 meter cube divided by 1 times 10 raised to the power of 6 centimeter cube. So that's just how we did that. We cancel out the centimeter cube here. So you end up with 125 times 10 raised to the power of negative 6 meter cube. So that's going to be the volume that we'll be working with. So yeah, I like to break this information down because I know that there are different students watching me with different capacities, and I think it's only fair that I go into detail. And if you're a student who, like if you feel like a lot of my videos are too in detail, you can always listen to it at 1.1 speed or 1.2 speed so that you can like just have it the details as a refresher but not as a major explanation in comparison to other students that might actually need that. So yeah, so change in Gibbs energy of mixing is simply equal to P. Now we can substitute P sub AR multiplied by V sub AR ln P sub AR divided by P sub T plus P sub NE multiplied by V sub NE ln P sub NE divided by P sub T. So that is it. So it gives energy of mixing. It's just simply 100 kilopascal, okay? Or I can just say 100. Remember, kilopascal is the same thing as times 10 to the power of 3 Newton per meter square. Pascal is the same thing as Newton per meter square. And since in this case we're dealing with meter cube, it is better for us to write, rather than kilopascal, we just write times 10 to the power of 3 Newton per meter square. That is the smarter thing to do, just because we need to be able to cancel out the units. So yeah, that's it so far. So 100 kilopascal or 100 times 10 raised to the power of 3 Newton per meter squared, right? Multiplied by the volume, which we know now to be 125 times 10 raised to the power of negative 6 meters cube or meter cube, multiplied by ln, the initial pressure, which is just 100 times 10 raised to the power of 3 Newton per meter squared, divided by the total pressure, which is just what we've solved, 200 kilopascal. So 200 times 10 raised to the power of 3, because kilo, right? Pascal, Newton per meter squared. So all of this information here, okay, plus the one for neon, because we just only wrote the one for argon so far, plus the one for neon, which is just simply 100 times 10 raised to the power of 3 Newton per meter squared. So that's the pressure of neon, partial pressure of neon, multiplied by the volume of neon, which is 125 times 10 raised to the power of negative 6 meter cube. Okay, that's that. Multiplied by ln 100 times 10 raised to the power of 3 Newton per meter squared, divided by 200 times 10 raised to the power of 3 Newton per meter squared. So yeah, that's it. Cancel out the meter squared and cancel out from the meter cube. So we just have the meters here. Cancel out this side, cancel out this side, cancel out the times 10 raised to the power of 3 times 10 raised to the power of 3, cancel out 100 here, 100 here, 2. So the same thing here, cancel out the meter squared, cancel out the from the meter cube. You only have the meters here. You cancel out the Newton per meter square up as well as down. Cancel out the times 10 raised to the power of times 10 raised to the power of 3 and times 10 raised to the power of 3 at the bottom. Cancel out 100 here, 100 here, 2. So 1 over 2 here. So after all this calculation, the change in Gibbs energy of mixing is just simply going to be 100 times 10 to the power of 3 multiplied by 125 times 10 to the power of negative 6. When you input that information in the calculator, you end up with 12.5, okay, Newton meter. And then let's not forget our ln 1 over 2. So multiply by ln 1 over 2. So all of that information plus the same exact situation here. 100 times 10 to the power of 3 multiplied by 125 times 10 to the power of 6. You end up with 12.5. Let's not forget our units, Newton as well as meter here. So Newton meter multiplied by ln of here is also ln 1 over 2. So when you input this information again, your calculator, you end up with the change in Gibbs energy of mixing is just simply 12.5 Newton meter multiplied by ln of half is just negative 0.69315, because anything ln that is a fraction less than 1 is always going to give you a negative number. That's the reason why I'm writing it out, just so everyone is like carried along. Plus 12.5 Newton meter multiplied by negative 0.69315. Changing Gibbs energy of mixing is just simply going to be, when you input this in the calculator here and this in the calculator here, we end up with negative, and you add them up, you end up with negative 17.32875 Newton meter. Remember, Newton meter is the same thing as what? Joules, because joules is just simply the unit for energy, and energy's fundamental formula is force times distance. Unit for force is Newton. The unit for distance is meter. So Newton meter is just joules, which makes sense because whenever we're dealing with enthalpy, entropy, Gibbs energy, we want our units to be in joules. That's how it's been in this book for like forever. So the change in Gibbs energy of mixing is just simply negative 17.32875 joules. But then again, we are scientists. We don't like to put our work in the we don't like to put our work in just the raw values. We want to put in the proper number of significant figures. So we have to look at the lowest number of significant figures that we used in solving this question. So going back to our work, we see that 250 is in 3 sig figs, and then 100 kilopascal is also in 3 sig figs. So we are going to approximate our work in 3 sig figs. So the change in Gibbs energy of mixing is just simply going to be negative 17.3 joules. And that is basically the answer to this question. Now, let's not forget, we still have another part to this work. And the other part to this work is that we have to determine the entropy of mixing. So now that we have the entropy of mixing that we have to solve, we have to go back to our knowledge of our knowledge from the Atkins Physical Chemistry 11th edition. In the book, we have a formula that connects the entropy of mixing with the changing Gibbs energy of mixing. So the formula is just the change in entropy of mixing is equal to negative change in Gibbs energy of mixing divided by T, which is just temperature. So the change in Gibbs energy of mixing is just simply negative minus, so remember there's a minus, the raw values, or which is 17, so negative 17.32875 joules divided by the value for temperature. Note the value for temperature in this question is just 0 degrees Celsius or 273.15 Kelvin. So divided by 273.15 Kelvin. So that is basically what's going on here. So you have change in entropy of mixing. It's just simply going to be negative, which is just positive, 17.32875 divided by 273.15 is just simply going to be 0.06344 joules. And of course, our question is requesting us to put our work in the proper number of significant figures. The previous question, which is the Sorry, the previous value, which is the change in Gibbs energy of mixing, is negative 17.32875. But we used the raw values rather than the approximated values, which is negative 17.3. So we have to use whatever the approximate value number of significant figure is. Like this question is in three sig figs. We use the same raw values here, but remembering that it is supposed to be in three sig figs. Anytime you have a science question, especially whenever you're dealing with chemistry or physics, you can't approximate your raw values to as a value to solve further questions. You have to use the unapproximated raw value in order for you to proceed in doing further calculations. Because if I use negative 17.3 in my calculation, it would, even though our work may be very maybe done properly, our answer is not going to be correct because we're not using the exact value or as precise the value we're supposed to use in calculations. All these significant figures, decimal places, all of these are very important in chemistry. So we have to use the raw value negative 17.32875 and not the approximate value. When we get to the end of our new calculation, then we can approximate. So we say with three sig figs, we're gonna have to have our final answer in three sig figs. So the change in entropy of mixing is just going to be positive 0.0634 joule per Kelvin. So that's going to be the answer to this question. Remember, the units for entropy is usually in joules per Kelvin. So yeah, this is basically the answer to this question. If you have any questions, suggestions, or concerns, please put it in the comment section. If you have a contribution to how can make these videos better, please also put it in the comment section. If you're a student who is struggling in any of your STEM related courses, whether you're in middle school, high school, or university, and you're trying to succeed, I am the tutor for you. I help students succeed in academia as well as to have the proper guide as they progress through their school life. So if you would want to book a tutoring session with me, make sure you email me at shahabitutoring@gmail.com. Besides physical chemistry, thermodynamics, quantum chemistry, I also teach a range of STEM courses. So do email me in order for you to book your first session. I wish you guys all the very best. Assalamu alaikum wa rahmatullahi wa barakatuh.